to another statistics seminar. We're opening our spring seminar series. So first, a little bit of a bio. So Dr. Gongjun is an associate professor in the Department of Statistics with a joint appointment in the Department of Psychology at the University of Michigan. He received his PhD in statistics from Columbia University in 2013. And his research interests include latent variable models like metrics, statistical inference, and divided. Fisher received the NSF Career Award, International Chinese Statistical Association, and Young Researcher Award for statistics. Words about the talk itself. So this is, we have an hour to finish the talk, and I'll, if Gongjun is willing to answer, you can feel free to call them. If you're on Zoom, please either submit your question in the chat or raise your hand.
Okay. Yeah, thank you, Emma, for the introduction. Yeah, it's a great pleasure to visit UW and give a talk here. It's nice to meet all the old friends and new friends. Okay. And today I will talk about this our new work of using this covariate-adjusted generalized linear factor analysis model with this application in education testing fairness problems. So this is a joint work with two of my PhD students, Jing Ouyang, Cheng Yucui, and also my colleague, Kim-Ming Tan. So Kim-Ming is also a UW alumnus, graduated here quite some years ago. So the motivation of our study comes from the application in this psychometrics field. So for most of you, I think are probably not very familiar with this topic, so I will give one slide to introduce this. So in psychometrics, particularly this educational and the sector. So we are interested in measuring these latent traits of individuals. Okay, for instance, like your mathematics ability, like your certain educational achievements level, or like your intelligence. Okay, now this is kind of just as any measurement problem. We want to just as for instance in physics, we want to measure the height or length of a subject. Then we use a ruler to measure it. Now similarly here, but the only difference is that the subject, the objective of interest is not observable, like our ability. So therefore, we need some psychological tools as an instrument. So therefore, we can measure these unobserved latent quantities. And typically, popularly used method as these instruments are designed these questions called such as standardized test. For instance, like GRE, SAT exams, many of us are very familiar with, are used to measure our this latent ability, or like this IQ test. Or many of us have this online personality test, right? So we use these answers to these designed questions, where here we will refer them as our these items. So the answers to these items, so therefore to make inference about this latent traits of interest. But of course, the problem is here, the measurement is not perfect. We have measurement errors, particularly, for instance, when we are answering a question, we have a chance to make a mistake, even though we know how to solve a mathematics problem, for instance, right? So we have measurement errors. And then, of course, because of this measurement error issue, we need statistical models to help us to use the observed data to make inference of this underlying latent traits. So here is a kind of a brief review of this history of some important works, not a complete list, but some of the important works in psychometrics field. Metrics field, actually, as you can see, because it's kind of coupled together with this statistical problem. So actually, it's started similar times with modern statistics. For instance, Francis Galton, we know, who kind of introduced this regression to the mean, this idea. now he was also the pioneer of this psychometrics field, and he was designing these survey types of questions to help measure people's intelligence levels. Now, of course, as we can see here, the target of interest, the latent traits, very naturally, since it's not observable, very naturally, we will need to use latent variable models. So here, latent variable, of course, referring to this variable not observable, right? So very naturally, people propose this factor analysis 100. So nowadays, vector analysis model is popularly used in statistics and machine learning, mostly as a dimension reduction tool. But actually, it's originated in the psychometrics field. There, actually, they started with the problem of defining these factors as this interpretable, representation of our kind of this ability or this general kind of, IQ, these types of interpretations. Okay. Now, with these types of models becoming more popular and many more people are studying these related psychometrics problems in around mid-1930s, Thurston and several other founders, they founded this psychometric society. So a funny, interesting fact is that the society actually was founded in Ann Arbor, at the University of Michigan in 1935 in September. So another interesting fun fact is that IMS, Institute of Mathematical Statistics, was also founded at Ann Arbor within about a similar week in 1935 in September. So like they are kind of born together like within the same week. Just a fun, interesting fact. So after that, of course, many other models like the item response theory model, which essentially is this nonlinear types of factor analysis model, and also these latent class types of models becoming popular in the psychometrics field. Of course, they're also, becoming popular in statistics and other fields. So as we are seeing, our goal here is to do this measurement. And there is an important issue is that to ensure this measurement invariance, which we can also here referring to as this fairness in many applications. In particular, for the latent variable, such as skill, ability we want to measure, we want to make sure that for two students who have the same ability level, they should have the same, probability of providing a correct answer to a question, right? So giving condition on this ability, their answer, the distribution of their response should be independent with their other covariates like gender, race, or other background information. That's, ensuring this fairness. In other words, we say a question, is fairly designed if two students with the same ability, then they have the same chance to providing correct answer. And in other words, if for a question, the same ability students, they providing the chance of get this question correctly, they are different, maybe depending on different gender or different risk factors, then we call this question, this as like a bias in the measurement issue. And for such types of questions or items, we call them as like these biased items, okay? So in other words, this, if there exists such types of questions, then we say this test is like not fairly defined, okay? So that's the fairness we are referring to here, okay? And our goal of this work is to use a statistical method to identify those biased items, okay, in this education testing setting.
That's a clarifying question. So I think what you're describing now is sort of like an item level fairness.
Yes.
Right, which I imagine implies sort of like an ability level fairness, or like a weight factor estimated level fairness.
Yes.
But I can also imagine that doesn't actually require item level fairness, right? So would you consider a solution where like maybe there are subtle unfair items, but they wash out in such a way that your like estimated abilities are still estimated in a way that is unbiased?
Because typically, if a question is biased, then they will affect your estimation result, introducing the bias in terms of estimating the ability, and other quantitative interest. So here, in order to control that, so we want to identify these kind of biased items. Okay, so actually, such types of problems have a long history in psychometrics field. So I borrowed this from Trent's, earlier slide. So this this is a famous kind of lawsuit, between ETS and insurance company. So it was sued in 1970s that ETS was sued for racial bias in lessening test for insurance agents. Okay, in particular, they were sued for favoring white applicants over minorities. Okay, of course, this took multiple years and got a settlement outside of the court in 1980s. But since then, actually, ETS had been started to adopt this safety guard to avoid such types of biased items. Okay, question?
That same assessed abilities, then the probability of scoring that question correctly, but how are the abilities assessed separately from the questions? So is this like, in theory, if you knew their abilities?
Yeah, so here it's kind of like we have the ability we want to measure. So it's kind of like a measurement problem. We have ability to measure. So we design these questions and as a, our tool to measure. So when we want to know mathematics ability, particular mathematics ability, then we design questions carefully. So therefore targeting on or like, from the design specs, therefore to control. Of course, they are like related. And here we are kind of assumes that we have design targeting on these abilities we want to measure. Okay, so now, of course, you will need like these statistical methods to help us to, avoid using such biased item, and this affects a lot of occupations and millions of, students and other, individuals. Now, fairness, since then becomes very popular, especially nowadays, we know, fairness is also, beyond education testing types of field, nowadays in machine learning, algorithm fairness is also important topics as where, studied popularly by many researchers. Okay, so in this talk, we will focus on the problem we just described. To give some more specific details about the model, so we will follow this item response theory model framework, which essentially is a generalized linear factor analysis model. Okay, since here for this education testing types of applications, the question is usually we have discrete types of categorical responses, right? So you get correct or wrong answers to each question. So for each individual here, we assume we have capital J number of questions. We get like this discrete, binary, for instance, responses to each question. Then we have like this J dimension binary vector for each individual, correct or wrong. And then based on that, we want to statistical graphical modeling kind of approach. We have this ability kind of generate these responses, right? Now here, this ability could be multi-dimensional, right? So you could targeting measure multiple kind of different abilities. Now, and then you will use this generalized linear types of factor types of analysis model to establish this relationship, and this is called item response theory in psychometrics field. Now, in addition to this latent ability, as we are seeing, so here we are also interested in these additional covariates that we want to know conditional on this ability, whether they are associated with our item response distribution, right? And that's a kind of the focus we want to study. If conditional on this ability, so I think there should be a kind of a line between the ability and the gender. So it's not connected. Okay. Some issue of this here. So it's like this ability and the covariates, so they could be correlated. So if they're independent, then the problem it becomes much simpler. Okay, so the part of our here mostly is handle the dependence. So you could have some identifiability issue and also make the theoretical study of the the statistical properties or estimation result more challenging. If they are independent, then the problem. So anyway, so condition on the ability, we want to know whether these are associated with our response. So if they are associated, then we see, for instance, in this plot, item 1, we would see it's a biased item. And in the psychometrics literature, this is also called like a diff item. So differential item functioning. So our goal, of course, is for those each of these dashed line, we want to know whether there exists such a connection or not. Okay, to formally introduce the model, we next computation is here. We assume capital N number of individuals, such as students. Okay, so we use I to denote the individual, ith individual, and J to denote the question, and we assume there are capital J number of exam questions, and we use Y to denote the response. As we mentioned, this Y, testing setting, mostly they are kind of binary or categorical, but of course, also have continuous response. So here we are considering this general setup. Your Y could be discrete or could be continuous. And so therefore, we use this generalized linear model types of framework. We assume there are some link function G here. forming the expectation function of our response conditional on the parameters and factors. And of course, now just as a DRM, so we could use logistic probability types of link for binary data and identity link for continuous types of response. Okay. Now this theta here we will use to denote this variable of interest such as the student's ability. Okay, so we assume there are k-dimension or latent ability, and in this study here we assume the number of latent factors is pre-specified. Okay. Now, we have xi corresponds to the covariates of interest, such as the background information, and we assume there are p number of covariates denoted by xi. Okay, and we use alpha and beta to. If in the factor analysis literature, alpha will be the factor loading vectors, and now with additional covariates x, then this beta will be the regression coefficients of x, conditional, conditional on these latent factors. So that for the problem of identifying this biased item, essentially under this regression framework, we are identifying these betas, these non-zero betas, right? So if this beta vector is 0, then that means like for that particular question, so x and response, they are kind of not correlated, right? So then essentially now our goal becomes to be a statistical kind of inference problem of identifying those betas that are non-zero. Okay. Right, so that's so again, so x and the theta, there's the edge connecting. I think that's the projector didn't show that correctly. Okay, so all right, so here we're gonna use y to denote the response matrix of n individual to these j questions. Okay, and this x as the covariance matrix. So y and x, that's what we observe, and the theta is the latent factors of interest not observed, and also the regression coefficients beta we denote as the B matrix corresponding to the biased item. These diff effects, they are also the regression coefficients we want to estimate, and of course this A matrix what we want to estimate. So in particularly, so in addition to the diff effect, so in many education testing settings, we're also interested in understanding this student's ability, right? So that's our eventual goal. So we're also interested in making inference for this theta latent factors or estimated theta. And also response theory, this actually it tells us about the information different. So A testing setup. So our goal here is like from a statistical perspective, we want to make statistical inference for this B, this theta and this A, given observed x and y. Okay, so that's kind of a general setup of the problem. Right.
Maybe this is another question for the end. Be also compare
Yeah.
changes to...
Yeah, that's a good question. So yeah, this is set, the setup we consider here. It's like we don't further consider the interaction theta and x. Right? So we could also, further consider this term. So this current setup is referred to as this uniform kind of diff setting. But we could also, to allow the further, non-uniform diff, literally they call that. And here in this work, we just start with this setting, but the method we could further generalize to this more challenging setting with additional interactions of this theta and x. Okay, yeah, that's a good question. Yeah. Okay, so next we talk about these challenges of this problem. So this model actually is not a new model. It has been used in psychometrics field, right? So and the challenge for this problem, the first one is as we just mentioned, so this ability they are latent, while on the other hand, the covariates they may this showing here, but there is X. So they are correlated. So therefore, first they will make this a beta have some identifiability issues. The literature, some method that people are using is like they just specify some items, maybe based on some prior knowledge or based on the domain, expert knowledge. So they identify some question that are not unbiased. They know they are not unbiased, pre-decided. And then based on there, they can ensure the identifiability and then do the estimation. And this is called, this anchor item approach. And those items that they know beforehand as unbiased as anchor items. But of course, as you can see here, such an assumption may be strong in many cases, and those pre-specified anchor items may be violated in practice, right? But of course, another types of method without assuming we know this anchor item, we could use this regularization types of method, because if you go back to the problem itself, you see, essentially it's like we have a regression problem. We want to identify some betas, whether it's a 0 or not, right? So it's kind of like this sparse learning kind of a problem. So just the add penalty, L1 penalty, for instance, for beta, and the estimation use the sparsity structure, right? So yes, that's also some method people used. But one challenge for that is like, especially for the larger dimension of data case, is that statistical inference is kind of quite challenging. So we know for high dimension data, so this debiased lasso types of procedure becoming popular, but those usually don't involve with this latent variable. So here we have additional latent variable. As we say, this latent variable and the covariates, they could be correlated. That makes the challenging part of this problem. So, and our goal is kind of to make inference when we have such latent variables in our problem setup. Okay. So we did some earlier work, but that's more in the classical domain setting. So here we want to generalize this to this larger scale types of data setting, where the number of individuals, number of questions, they can both go in large. Okay, so the observed response matrix Y is a kind of going large in 2 dimensions. Okay, so the individual large and the number of questions large. This consistent with many of testing problems in this model. One example of this PISA study, which involves more than 600,000 participants from like about 80 countries in the region, and involves about 500 number of questions, right? So even though it may not be as a large scale compared with this, machine learning or deep learning types of applications, but in education, quite large scale data, right? Because we involve collecting data from all these individual students, that's kind of a lot of efforts. So, so here we consider the setup of the both dimension that goes large. So that's the large scale we are referring here. Okay, so traditionally for such types of latent factor analysis model estimation, usually people treat latent factor as random effects. But the problem is that if you do this random effects kind of modeling, then likelihood-based estimation, particularly you want to maximize your marginal likelihood of the observed data, you involve this integration of integrating out those random effects. So here corresponds to the latent factors. So now scale data, of course, right? Since you involving a lot of these integrations. So that's why, for this high dimension data factor analysis, typically instead of treating the factors as random effects, people treat them as fixed effects. Okay, so if we are treating these factors as fixed effects, in other words, we're treating them as model parameters, and the likelihood becomes much simpler, right? So if you're doing EM algorithms, right? So the complete likelihood that involve this integration, and if you directly maximizing this, it's much easier. But of course, we know in the classical setting, the individual goes large, the number of questions is limited. This leads to inconsistent estimation. If an individual only answers 5 questions, it's hard to consistently estimate this individual ability, right? Scale setting, where a student, for instance, right? So this, you can collect enough information with the student, then without treating this as a random effect, you can still consistently estimate this this latent factor and of course the related covariates. So that's why, when handling this high dimension kind of data in the factor analysis literature, people usually treat these latent factors. So for instance, this is not only in the field, but also in econ and the statistics literature. kind of related to some problems like matrix completion, right? So for matrix completion, some method they also use this low rank matrix decomposition, which essentially is a factor analysis model kind of assumption. So essentially it's also doing factor analysis here. And there mostly people treat like fixed effects decomposition.
Can you go to the previous slide? In your for the likelihood.
Yeah.
Are we thinking about beta right now?
Yeah. Other covariates, yeah, the beta and alpha, yeah.
For example, like this consistency, this is already established for fairness with alpha and beta.
No, yeah. So this consistent, that means like when we don't consider this, people have some result about. Do some literature review in a few slides there.
Okay.
Yeah.
So we do have alpha, right?
Yeah. We do have other things included in the
Okay.
Yeah.
But
Yeah. Everything is there.
beta.
Yeah. Okay, and also, recently people are also using these similar types of models in genetics, for instance, but there, like some of the work use these latent factors to adjust these confounding factors. Now, here, one difference is here for our application, these latent factors, we have particular interpretations. For there, like if you want to extract this latent factor to adjust the latent confoundings, then most of the time they don't care, the interpretation of the factor itself usually is less of interest, right? So here more this latent factor as well as this regression coefficients jointly. But the model that kind of share is shared by applications in different fields and as listed here. So now for these types of latent factor generalized latent factor analysis models, so the challenge is that most of the work in the literature they focus on linear models. Right, so and particularly for doing statistical inference, right? So if you do this linear factor analysis model, there are a lot of works earlier on making about the limiting distribution, the statistical inference results with or without these covariates. But for these nonlinear types of generalized linear factor analysis models, only recently people studied the case where they only have this latent factors but not the covariates for the statistical inference. And the inference for involving this both, latent factor and the additional covariates. So that's actually still remains an open problem. Now in this work, that's kind of the problem we want to address. Particularly, we want to consider the setting. We have this double asymptotic regime where the number of individual and number of questions both going large. And the nonlinearity, of course, introduces these challenges. So therefore, many of these linear kind of matrix decomposition methods will not apply here because we have this additional nonlinear transformation. Okay. So another issue, as we mentioned here, so because we're introducing this covariates, identifiability becomes the issue because the covariates and the latent factors, they are correlated. And since there's a limited inference result, and we want to make statistical inference. So that's what the problem we want to address. So we don't need anchor items, and computationally, since we use the fixed effects types of model, it will be more efficient, and we want to make valid statistical inference under this double asymptotic regime. Okay, so here is going back to here. That's what we want to infer. This beta, theta, and a. Okay, again, this theta and x they're connected. All right, so the first issue, as we said, is this identifiability of our model. So now, we know if the model does not cannot guarantee consistency of the estimation, and of course cannot do statistical inference. So for model identifiability, it means that for two sets of parameters, if they lead to the same distribution of our data, then these two sets of parameters must be the same. Since otherwise, based on the observed data, we cannot distinguish these two different sets of the two sets of parameters, right? So even if you have an infinite number of sample size, you cannot do that. So therefore, you cannot have a consistent issue, right?
For your problem, do you just want the data? Do you need identifiability of data?
Yeah, that's a good question. I will I'll talk about that in a moment. So yes, if you just want the identifiability of a beta, so actually the theta, the identifiability of theta can be, we don't require that. But still, for beta, we need some identifiability condition. But as I mentioned, in this application, we are interested in not only beta, but theta and also this factor loading matrix. So we will propose like two identifiability conditions, one for beta and one for theta. Okay. So that's what I'm going to discuss in this slide actually. So now the identifiability issue following the form of the mean function form. So you can see first for any set of parameter alpha, theta, and beta, if you do this linear transformation involving this T matrix. So you say you transform beta to this beta tilde, and you transform theta to this theta tilde, then this leads to the same value of the right side of these two equations. So therefore, this beta, theta, and theta tilde and beta tilde, they are identifiable in this is up to this linear transformation involving this T matrix. Okay. So that's the identifiability issue for beta. Now, this identifiability issue, as mentioned, is a kind of because it's kind of coupled together with the indirect effects of x to theta, then to y. Because theta is not observed, so these two, they are kind of coupled. I know many people are doing causal inference, probably you are more familiar with this with me, but that's kind of the issue caused this. So, in other words, if we assume theta and x they're independent, we don't have such an issue because by adding this t, you have theta tilde and x. If you originally theta x, they are independent. Theta tilde after adding information of x, then becomes not independent. Theta and x, they are independent. Then we don't have identifiability. Only because theta and x correlate, we don't know the correlation structure. Then it's an identifiability issue, right? So that's a kind of the key part. Another identifiability issue, which is a kind of the classical feature, which is the factor rotation, right? So we know for factor analysis model, usually you have this non-identifiability issue if you put any invertible matrix G and G inverse between the factor loading and factors, they have the same result, same distribution of your data. Then this leads to the identifiability issue of the factors. That's kind of what people understood pretty well in factor analysis literature. Now that's the second issue. Now related to the question just discussed. So as you can see here, if you add this factor transform T and alpha here, actually you result this beta check. Now for this beta, actually it will cancel out and be the same as our beta tilde here. That means the identifiability rotation factor does not affect our beta. So beta only identifiability issue, while the second identifiability issue related to G, that's more about these factors and the factor loading structures. Okay, so therefore, if we only want to make statistical inference for beta, so we don't need to care about this factor rotation. We want to do both. So that's will lead us to discuss the following identifiability conditions. First is for the beta, the other one is for the factors. Now for the beta, as I said, without additional constraints, beta and the true beta star denoted as beta star, the true beta denoted beta star, and any linear transformation involving this T matrix, this any T matrix. So they will be kind of in the equivalent class, right? So they will lead to the same distribution of our data. So we need some additional constraints, so therefore we can separate them, right? We can separate them. And here we will use this minimum L1 condition proposed in one of our earlier work. So this condition, the good thing of this condition is that it's satisfied if the unbiased items in your data set, they are majority, okay, and which practically live. So it's like we will usually believe, since the question is usually very carefully designed, the biased item we usually they are less majority, less than 50%, for instance, right? So here I'm not seeing it's sparse. The proportion may not go to 0, but I'm seeing it's less than 1/2. Okay, less than 1/2. So if such types of conditions are satisfied, then we could have this condition, and so therefore guarantee the identifiability of beta. So we choose this condition mainly based on this practical kind of nice interpretation. So here, this condition holds if the biased item is smaller than constant. So here, this constant is not going to 0. Okay, so this proportion is not going to 0. So it's different from the sparse kind of where we usually assume like it's high dimension, the sparsity level goes kind of proportion goes to 0. So here you could have like for instance in the unit, suppose in this example of this unit dimension case, this condition holds if you have half of the questions they are biased. Okay, you could further relax this with additional constraints, but this is kind of it's a very reasonable assumption, and we will follow this one. Okay, so we as I mentioned, so we could allow this data types of setting. So we want some structure, but this non-zero ones that we it's kind of it's not like going zero proportion. Okay, and theoretically this will guarantee help us to ensure the identifiability of beta. So therefore establish the consistency and later the inference result. Okay, so the second issue is for the factor rotation. Now, of course, this is kind of very well studied in the factor analysis literature. So for convenience here, we will follow the setup listed here. So we assume these latent factors, they are uncorrelated, and this also this A star transpose A, we follow this diagonal structure. But of course, you may this is a too strong assumption because your latent factors could be correlated, right? So we could replace this by some other commonly used constraints in the factor analysis literature. For instance, we could not put in constraints on the latent factors. We allow them to be correlated, while we can put additional constraints for the latent, for the factor loadings, right? So again, because in the education testing setting, you design question to measure these latent factors, you have certain ability to control your loading matrix. For instance, you have a scale 1, scale 2, scale 3. Maybe you just design question 1 only related to scale 1. So you have certain kind of a sparse constraint for your factor loading, right? So therefore, these types of constraint also popularly used in kind of some parametrics field. Now, with this kind of additional constraint, we can guarantee the identifiability of the factors and the factor loadings, right? Okay. So in general, it's like for any types of factor, the identifiability issue. So you can find this kind of transformation. So after such a transform, the transform parameter satisfy the proposed identifiability conditions, right? So therefore, our result can be inferred to any other true parameter set up to this transformation, right? So we will study the property based on these two sets of assumptions, identifiability assumptions we proposed here, which we believe align pretty well with the application, with the practice. So now for the estimation, because we use this fixed effects model, so we can do the updates, estimation updates iteratively. So we're giving this latent factor and B, we update the factor, and then giving factor update the regression coefficients, right? Because we are under this GRM types of framework, if you're giving these latent factors, then estimating the factor loading and regression coefficient, then that's like a GRM estimation problem, right? So in each step, this can be done rather efficiently. So we can just iteratively update that. And after the estimation, then we do additional transformation. So therefore, satisfy our proposed identifiability conditions. Because from step 1, we only find like one within this all equivalent non-identifiable set, and then do some additional transformation to make them close to make this estimator satisfy the proposed condition identifiability condition. So therefore, hopefully this will give us consistent with the true parameter which assume satisfy these identifiability conditions. Now, of course, the first one is minimizing this L1 problem, and the second one is we do this diagonal rotation transformation. Okay, so that's the estimation procedure, and then based on what the identifiability conditions, we can establish the following, consistency result. As we mentioned earlier, this one challenge coming from this nonlinearity, right? So we cannot use the usual, linear model types of factor decomposition types of techniques, but rather we need to work with this likelihood to handle the nonlinearity. And another issue is like incorporate this identifiability constraints into the estimation. So that's another tricky part in the theoretical result. So so here we consider we allow this P goes large, but as you can see here, for our estimation we didn't introduce additional kind of regularization. So therefore, as expected, you cannot go too large, right? If you want P goes much larger than N, for instance, you will need additional regularization for your beta, right? Add some additional L1 or other types of penalties. But since this problem is already challenging enough, so we start with this, more. But for the estimation, we don't put additional constraints, penalties. And under this setup, we can show the consistency of our estimation, like these factors, factor loading, and also our regression coefficients, like the diff effects. So this is kind of like near optimal, particularly if P is fixed. If you consider the case P is fixed, J goes to that will be kind of like optimal, near optimal. So for instance, as you can see here, if you look at the estimation result for the factors, now if you consider the oracle case where you know the factor loading and you know, then for each individual, the goal is just to estimate the factor. Now each individual answer the J question, then the error rate by logistic, J. The error rate for the first term here is consistent, kind of consistent with this log n divided by J term. It's up to this log term, this log n divided by J. Now, in practice, typically, at least for this education setting, we usually have n much larger than J. In that type of setup, the second term will be kind of dominate the first term. So in that sense, the estimation of theta is kind of close to the optimal kind of rate. And similarly, you can see, for beta, if you know all the latent factors and if you know the A, this is the question any individual optimal rate, of course, is a to n. And now this will kind of corresponds to this term here, while you will have an additional J term that's corresponds to the estimation of these factors, kind of have an additional term there. Okay. Now, in addition to this consistency, we can further establish the normality of our estimation result for our factors, for our factor loading, and also for the regression coefficients like the diff effects. Okay, and also the covariance matrix can be consistently estimated. So therefore, we can use the result to do hypothesis testing and to construct confidence intervals and so on. Right. So that's our main theoretical result here. Oh. Yeah, so K we assume is fixed. The number of factors we assume is given fixed. And the P here we allow is good, but it's rather. The last one. Yes. So you can consider a linear combination of this and a linear combination of this converges. Yeah, here presentation I just use this kind of informal notation. Yes, thanks for finding that out. Yeah. Okay, so we have some simulation result to illustrate this. So we generated our factors and X from this normal distribution. We consider different settings with all X and the factors, they are independent and up to 0.7 correlation. Okay, and also we consider here different sample size from 300 to 2000 and different P, not that large, 5 to 30. Again, since we don't add additional regularization, so we don't have P goes very large dimension, and K is taken 2, and J, the number of questions is 100 to 500. And our goal in the simulation, we focus on testing the regression coefficients for X, right? So we consider 2 different settings. One is this sparse setting, where for each covariate, there are like 5 out of J questions, they are biased. So that's kind of sparse. The dense setting is like 20% of the items, they are biased. Okay.
When P is small, so you're going to have dependence between theta and X.
Yeah.
And it's like a non-trivial dependence for small P. Is that right?
Yeah.
Right. Whereas like as P gets very big.
Yeah,
like
when P gets big, the problem definitely becomes more challenging, right? So that's why we'll see, if P gets big, so in order to handle this, we need some additional structure between X and the theta, and also maybe we need to add some regularization terms,
okay.
Right?
But if K got bigger, wouldn't this actually get easier? At least like the way that you're generating this covariance?
Not necessarily. Yeah, because here we assume K is fixed, but in general, if you have K also allows it goes to infinity, the problem becomes more challenging.
Yeah.
Right.
But
so
I'm just, I guess, like, because the structure of the sigma ij like doesn't have a phase transition, when it goes from the dependence between thetas and x's versus within
Ah.
thetas versus within x's.
Yeah. You
So
could,
it's
you
really
could,
discriminate.
yeah. You could try like different settings. So here is like for simplicity, we just try this one. Yeah. We could, you could be different. Like so. Yeah. So here is some, just the simulation results. We show, the type 1 error can be very well controlled for each, hypothesis testing, and of course, when you have a rule here corresponds to the strength of the non-zero beta. Okay, so of course, if you have a larger signal, the power will be higher, right, for the hypothesis testing. And also, when you increase the number of covariates, here it seems quite robust. So when
This is power for what? For what test?
Oh, so this is the testing problem. It's like yes, for beta. So we focus on beta. So for each covariate and each question, we want to test this covariate whether it's biased for this question, right? So and then we kind of aggregate all the results together and present in this graph. It's kind of treating as a hypothesis testing types problem. Now also, the sparse versus dense is kind of a dense setting is a bit challenging, but lower power, but rather robust in this case, I used to say. And here, next we talk about this application setting of this PISA data. As mentioned, it involves like 600,000 participants from about 80 countries and 500 items, and it has a kind of like 3 components: reading, mathematics, and science. So very naturally here we will choose the 3-factor latent factor analysis model. Each corresponds to one kind of component. Okay. Now we of course also collect some information of these individuals. Now for illustration here, we only analyze a subset of the full data set. Okay, so here we only focused on the students from Taipei, and there are about 6,500 students and about 200 questions. And there are like, we consider 10 covariates, including information about the gender and the school kind of information, whether it's a private or public school, or whether the school is in the urban area or like a suburban area. And here latent factor is 3. And another thing we didn't mention much is like for practice, for real data, usually actually there are some systematic kind of missing in response. This comes from the design of the problem, because even though we have 500 problems, but it's a kind of not practical to ask each student sitting there and answer all the 500 problems, right? So usually they kind of use block the designs, design different kind of test components, and for each individual, they maybe just sample different components and maybe ask the student answer part of this question. So therefore, there will be some missing coming from the design, and the method we introduce can be naturally handle such types of missingness, and so we'll directly apply our result.
Is it mPower, or is it like the computer is like sampling questions based on their performance so far?
Oh no, here is not like that. So that is kind of pre-decided. Okay, so the one you mentioned today is like a computerized adaptive testing. That's kind of based on your previous result, then you assign. Yeah, and we're not doing that. We are here is like we have already maybe like 10 booklets or 20 booklets. You already specify that. Yeah. Okay, so here is the result for gender effects. Positive means like it's kind of a male, and negative more female, and there are a lot of others that are covering 0. Yeah, the predictor not showing that, but but there's a lot of them because we have like 200 questions, right? So there are like about 10 out of these 200 we have kind of a significant not covering this 0. Here we did a buffer-only correction too, because we are doing multiple kind of testing. And for again, there are some lines. So this question here corresponds to some bird question, and this question here corresponds to so this question is kind of boys kind of maybe more like to do stuff with birds and caterpillars, and then they are kind of have some bias towards these questions. But of course, in order to make sure whether there do exist such kind of bias, we may need to work together with the educational experts. Here is just from statistical analysis. These questions are detected, and the seems kind of may have certain interpretation. Huh? Yeah, we don't have the content of the item, but we know it's, only know, what it's about.
So if I'm counting correctly, you have 11 items that are highlighted out of 200.
Yeah,
It's about 5%, which is the overrate.
Yeah, yeah, could be, but
They said you don't run.
yeah, we did buffering correction. So that may not be exactly like yeah. So yeah, but of course that's definitely, as I was saying, this is just based on the hypothesis testing result what we, but of course we need to work together with experts to further to say whether there is real evidence or not, right? Okay. All right. So there are some other examples. Here is like a public school and versus kind of a private school. Again, we detected some items, right? And also, this is the urban versus this like a rural area kind of school. So last thing I want to mention about is just for a comparison. So because sometimes people ask, why we just do a logistic regression without including these latent factors, right? So here is a result to illustrate that. So the left-hand side is the result. We just do a logistic, types of regression without including latent factors. Because for these types of calculation, we know since the question is designed to measure these latent factors, without including this, they definitely introduce bias. And you can see here, you detect way more kind of biased items than if you control these latent factors, which you're supposed to measure by this question, right? Just to illustrate this point. And similarly for this urban area, if you just do logistical, logistical regression, so here, this is the binary response, it's logistical regression, then you have nothing, but rather you get some additional detections if you consider this latent approach. Now, from conclusion, so here we study this kind of statistical inference problem for this covariance-adjusted latent factor analysis model under this kind of large-scale setting, and we introduce this interpretable identifiability conditions and study the statistical properties of the estimators under the proposed identifiability conditions. Of course, the future work, as mentioned, we could generalize the result to this high-dimensional covariance case, right? So we could add, additional L1 penalty for the beta, and then add additional, debiased lasso kind of approach to make inference for beta, right? To incorporate this additional high dimensionality for covariance. And our simulation result shows it works pretty well in such setting. And of course, we could also, for the practice, we have like a missingness. So particularly if you include many of these covariates, because they also have this survey types of question to collect information. So some of the covariates may also have like this missingness issue. So of course, to study, this missingness in covariates and also, in response, that's also an interesting work to further pursue. Okay, thank you. Yeah.
I thought I'd sort of a philosophical question in line with some of the questions that you've got. So, and just the degree to which hypothesis testing is maybe not the most reasonable thing to do, and maybe confidence intervals would be better. Yeah, sorry, I'll stop.
Yeah, yeah.
So if I'm ETS, right? I would much rather not, like, I'd much rather think that all my items are unbiased, right?
Yeah.
So I should assume that like K is really big, right? And I should use like a really small sample. I'll be really underpowered, and I'll say nothing, and I want to do the most strict bond for any correction, right? Nothing is biased.
Yeah.
Right. And instead, it seems like maybe like this is a case where the null is not really like the null is actually the preferred outcome.
Yeah.
And so I wonder if instead it would make more sense to say, like, if there's an item with a bias that exceeds some amount, like we decide that it's biased, and then any item whose confidence interval includes that, we
Yeah.
Right?
Yeah, I think
a really wide interval, but includes
yeah,
zero,
that's a
problematic item.
Yeah. That's a very good point. I think practically, I think they do have some types of rule. It's not like directly used what we presented here. Yes. Yeah, exactly. They have some kind of practical kind of rules like that. That's good point. Yeah. Yeah, you can go ahead.
So it seems like the point of this particular study was to identify problematic items, right?
Yeah.
But could it be turned around and used to estimate student level of For all these things, you gotta work with time.
Yes, exactly. Yeah. Yes, we could. Yeah, we could also do that. That's why we were seeing, okay, we can do inference also for data. So therefore, we can adjusting this biased item. We can have a better estimation for the for instance. Yes, thanks.
And this already does that, right?
Yeah, this already does that. Yeah. We are still writing the paper. Yeah, we will add that to emphasize that. Thanks.
My question was, it's all interesting, but visual items about the bias, because you only care whether the test overall is the sensitive of bias or not. So the overall effect of data X might be interesting. So maybe we can these guys out. So would it be interesting? I mean, it's very stringent to identify individual items. This might be actually impossible to do that. So maybe the overall effect.
Yeah.
So that's overall data. And
Yeah. That's a good question. Maybe based on these types of result, overall kind of a matter, and like based on that, to do.
this items is now picked out, combine the effect, maybe the effect is most likely the effect is significant, but maybe
Yeah, could be. Yeah. Here is like yes. Yeah, exactly. Yeah. We could, also try to form, test, for instance, like hypothesizing types of kind of that overall, you say the overall bias of all the items, right? The global kind of testing all the data combined together as global test, right? So we could, based on the test the statistical. Yeah.
That would be, I think,
Yeah.
assumption that the total number of items is equal to infinity, not the number of items that each individual student answers.
Yeah, so it's kind of like we need like because especially if we have a missing data case, we kind of need each individual, the number of responses kind of goes to infinity, even though it could relatively go to infinity at a slow rate. So it's just like when we apply central limit theorem, maybe we say, oh, 20, 30 observation is good, right? So here similarly is like maybe like a regime, right? So it's like maybe each is already this asymptotic regime kind of approximate that well, and based on empirical result, it seems so. So yeah.
I guess my question was about the constraint that you're using for
Yeah.
So I wonder, so there's two kinds of questions. The first one is about how to interpret that in practice, because when you approach this from a pre-design point of view, by setting some beta equal to 0, you're essentially saying, these items are not biased, and they remain main.
Yeah. So here, yes.
But you have actually dealt with this problem in the mirroring here, but you're anchoring items.
Yeah. Yeah, that's like what we are doing. What we are that.
So that's
Yes. Yeah. For instance, here is like here is the example. Suppose we only have one X. If there are like 50% of beta, they are they are like 0. Then that's fine. That this condition is satisfied.
But something like 50% is like a really large. So
could have it larger than 50% if this beta is kind of symmetrically kind of distributed. So therefore, kind of like that. If you not all biased towards one direction, if you have a bias towards this direction, the other direction kind of balance well, then you could have more than 50%. But
it also needs to depend on the dimension of the.
Yeah. Also depending on the dimension. Yes. Exactly. Yes. So here it's sufficient, but not necessary. So But for education kind of setting, because typical people, because this question, they are kind of carefully designed already. So 50% maybe is kind of reasonable for this particular. But of course, we make it whether there are kind of relax such types of requirements. Yeah. Yeah.
I just does it get better or worse?
When it's going on P, we can get a kind of a similar result, but we need kind of, as mentioned, some kind of symmetry, kind of, you're not biased towards one direction, such kind of constraints. Yeah. Larger the P, since you have more things to consider, it makes it a bit harder. Yeah.
Let's thank our speaker.
Yes, thank you.